BioVivacious, I'm Sebastian. BioVivacious is a YouTube channel dedicated to clear fundamentals of biosciences and make the subject exciting. In an earlier video, we have seen how glucose is converted to pyruvate through a process called glycolysis. Glucose is not the only carbohydrate we consume. We consume polysaccharides, we consume disaccharides, and we also consume other monosaccharides like galactose, fructose, etc. Or they may be the endogenous metabolites. So we are going to see now how these carbohydrates other than glucose enters into glycolytic pathway. So this pathway is called feeder pathways. So initially let us begin with the feeder pathways for monosaccharides. We begin with the feeder pathway of galactose. So galactose we get mostly from milk, and this galactose enters into the mainstream glycolysis through a pathway known as Leloir pathway. So it was discovered by an Argentinian scientist called Luis Leloir, and he was awarded Nobel Prize for various discoveries, his contribution to biosciences. So it begins with the galactose. Now remember, galactose exists in the beta configuration. So at this is the fourth carbon atom, this is carbon number 1, and the first carbon atom, this will be the hydroxyl group, so therefore beta D galactose. So fourth carbon atom, this is how it is different from glucose. So therefore this is, first of all, it is getting converted to the alpha form. Since space is less, I will not be drawing the structure, I will just write the names. So therefore we have a beta D galactose. Now this beta D galactose is converted to alpha D galactose. Okay, so the name of the enzyme is mutarotases. Mutarotases is the enzyme. So therefore it is an epimerization reaction. So this is a major reaction, epimerization reaction, which will convert beta D galactose to alpha D galactose. The next step is to convert alpha D galactose to its phosphorylated form. So that is catalyzed by an enzyme known as galactokinase. So galactokinase, I am not writing the full thing, galactokinase, that requires an ATP to ADP conversion. So ADP conversion, you will have galactose 1-phosphate. At the first position is phosphorylated. So once you have galactose 1-phosphate, now at the same time there is another reaction must occur. That reaction is, we will take a glucose 1-phosphate. Glucose 1-phosphate. So glucose 1-phosphate, this has to be converted to its energy rich form, and that is done with the help of a UTP molecule. A UTP molecule is added to this, and the 2 phosphate groups are removed from UTP. So it becomes a UMP that gets attached to glucose. So therefore it becomes UDP glucose. It becomes UDP glucose. The name of the enzyme which will do this conversion is UDP glucose pyrophosphorylase. Pyrophosphorylase. So this is another important step. So you get UDP glucose, which is an energy rich molecule. At the same time you also have galactose 1-phosphate. Now what is going to happen is this galactose 1-phosphate Okay, this galactose 1 phosphate will react with this UDP glucose. Okay, and then it becomes UDP galactose. Okay, it becomes UDP galactose. So if the UDP is left here and the galactose is given and the glucose is transferred here, and this becomes the real glucose is transferred. So I'll write it like this: glucose, it will continue to be in green color. It becomes glucose 1 phosphate. The phosphate is from the original galactose 1 phosphate. So it becomes glucose 1 phosphate. And this reaction is catalyzed by an enzyme known as, it's a long name, it is UDP, galactose alpha D galactose 1 phosphate, that is UDP galactose and alpha D galactose 1 phosphate uridyl transferase. Okay, so basically for all practical purpose, you remember uridyl transferase is the enzyme. Galactose 1 phosphate, it is UDP glucose. UDP glucose, GLC. UDP glucose, alpha D galactose 1 uridyl transferase is the enzyme. So you will get UDP 1 glucose and UDP galactose. Now what happens to this UDP galactose? Now this UDP galactose is converted back into UDP glucose. UDP galactose is converted back into UDP glucose, because you know that conversion of galactose into glucose is only a change has to occur only at the 4th position. So therefore this is catalyzed by an UDP galactose 4 epimerase. UDP galactose 4 epimerase. So this is also an important reaction. So therefore this UDP glucose is taken care of, and this way the reaction can continue. So we are left with the glucose 1 phosphate. And now you know that glucose 1 phosphate can be converted to glucose 6 phosphate. Okay, glucose 1 phosphate is converted to glucose 6 phosphate, and the name of the enzyme is phosphoglucomutase. Phosphoglucomutase is the enzyme, because it is shifting the phosphate group from the 1st position to the 6th position. So, and it is an isomerization reaction. Now look at the most important reactions that are happening. There are about 5 important steps. So the first one is this epimerization reaction, and the second reaction is this phosphorylation reaction, and this is the third reaction. The third reaction is a transferring of a phosphate group. Okay, so this is a third reaction, and the fourth reaction is this reaction, an isomerization reaction, and this is the 5th step, that is an epimerization reaction. So therefore we have an epimerization reaction, we have a phosphorylation reaction, we have a transferase reaction, we have an isomerization reaction, and we have an epimerization reaction. I know that due to lack of space I have not drawn the structure, but this is how galactose will enter into the mainstream glycolytic pathway with the formation of glucose 6 phosphate. So also count the number of enzymes that are required for this particular pathway. There is a metabolic disorder associated with the galactose metabolism, especially this particular enzyme, this uridyl transferase enzyme. People who have a deficiency of this uridyl transferase enzyme, so what will happen is this galactose 1 phosphate cannot be converted to glucose 1 phosphate. So therefore galactose 1 phosphate concentration can go up and galactose concentration can go up in their body. So when these intermediates are getting accumulated, which can be harmful to an individual, harmful in a sense it can lead to diarrhea. It can lead to liver damage, liver cirrhosis, and at times it will lead to mental retardation. So therefore, this intolerance to galactose due to a deficiency of uridyl transferase enzyme is known as galactosemia. Okay, galactosemia is due to the deficiency of uridyl transferase enzyme. Now, there is something else associated with the galactose metabolism. So we know that we all can tolerate milk, we can digest milk, we can digest galactose. But people, as they get old, what is likely to happen is, let us look at the structure of galactose. I am writing. This is galactose. H, OH, OH, H. This is galactose. See, the eye, the lens of the eye, etc., has got an enzyme known as aldose reductase. Aldose reductase. So, with the excessive consumption of milk at an old age, so what will happen is, if the galactose is not properly metabolized, then galactose will be converted to reduction occurs. Reduction of galactose occurs. So you will have this product. So this is called galactitol. Okay, galactitol. So galactitol is the reduced end product of galactose metabolism. Now remember, galactose is galactitol is an osmotically active substance. So you have NADPH plus H plus, and this will result into NADP plus. Okay, so it is an osmotically active substance. So this osmotically active substance leads to accumulation of, it will draw water to itself. So therefore there is a possibility of clouding of the eye taking place. So that's why elderly people are not highly advised to consume a lot of milk at an adult age. It can lead to, or it can precipitate cataract. So now let us look at the overall equation for galactose metabolism, or either feeder pathway for galactose. So therefore we have seen galactose plus ATP, that will result into glucose, right, glucose 6-phosphate and an ADP. This is the overall balanced stoichiometry for galactose metabolism. Now let us see how fructose enters into the feeder pathway of carbohydrate metabolism. So in adipose tissues as well as in muscle, fructose will be acted upon by hexokinase enzyme. Acted upon by hexokinase ATP, so ADP is formed. Inorganic phosphate is attached to fructose, it becomes fructose 6-phosphate. Now we know that fructose 6-phosphate is a regular intermediate in the glycolytic pathway, so it will continue with the glycolysis. So the story is very simple. But when it comes to liver, fructose has a different pathway altogether, where it involves about 6 enzymes for converting or making fructose to be part of glycolytic pathway. So what will happen is, let's begin. I'm not writing a structure once more. Fructose will be converted to fructose 1-phosphate by the activity of an enzyme known as fructokinase. Fructokinase. Remember, this is happening in liver. Okay, fructokinase. So therefore, that also requires ATP and ADP. So fructose 1-phosphate is formed. Remember, fructose 1-phosphate is not an intermediate in glycolytic pathway. So in glycolytic pathway, we had an intermediate called fructose 1,6-phosphate. But we cannot even convert this into fructose 1,6-bisphosphate because there is no specific enzyme which can act on fructose 1-phosphate. So what is the next alternative? It is to cleave by enzyme aldolase. So therefore, fructose 1-phosphate aldolase. Remember the aldolase we came across in glycolysis. It will cleave fructose after carbon number 3, between carbon 3 and 4. So you are going to get one of the product which is not phosphorylated. That will be glyceraldehyde. Glyceraldehyde. Okay. Now remember, glyceraldehyde structure is CHO, CHOH and CH2OH. This is the structure of glyceraldehyde. Now the other product is dihydroxyacetone phosphate. That is carbon number 1, 2 and 3 become dihydroxyacetone phosphate. 4, 5, 6 has become glyceraldehyde. That is by the activity of aldolase enzyme. Now this glyceraldehyde can be converted to glyceraldehyde 3-phosphate. So we know that glyceraldehyde 3-phosphate is an intermediate in glycolytic pathway. So therefore an ATP is used to do this conversion, ADP, and the name of the enzyme is triose kinase. Triose kinase. Okay, triose kinase will act on it and becomes glyceraldehyde 3-phosphate, which can be an intermediate in glycolytic pathway. Now what happens to DHAP? Okay, I'll come to DHAP. Let us see the next fate of glyceraldehyde. I'll use another pen. So next possibility is glyceraldehyde is converted to glycerol. Okay, glyceraldehyde is converted to glycerol. Now remember, this is an alcohol, this is an aldehyde. So therefore you have an enzyme which is an alcohol dehydrogenase. It is an alcohol dehydrogenase and it is an NADH dependent enzyme. Okay, 2 hydrogens are added, you get glycerol, an alcohol dehydrogenase. Once you have an alcohol dehydrogenase, this glycerol can be converted to glycerol 3-phosphate. It is phosphorylated at the third position. Glycerol 3-phosphate. So therefore an ATP is used, ADP is formed, ATP is used and ADP is formed. Name of the enzyme is glycerol kinase. Glycerol kinase is the enzyme. So you have glycerol 3-phosphate. Once you have glycerol 3-phosphate, look at the structure of glycerol 3-phosphate. Glycerol 3-phosphate is very easy to be converted to dihydroxyacetone phosphate. Okay, so therefore it's a matter of just removing 2 hydrogens, and those 2 hydrogens are removed by, I'll put it this way, removed by one NAD plus removes that as NADH plus H plus. 2 hydrogens are removed and the name of the enzyme is glycerol 3-phosphate dehydrogenase. Glycerol 3-phosphate dehydrogenase. So these are the steps by which fructose can enter into the mainstream glycolytic pathway in liver. Let us count the number of enzymes. So here is enzyme number 1, here is enzyme number 2, and here is enzyme number 3, enzyme number 4, enzyme number 5, and this is enzyme number 6. A total of 6 enzymes are required for making fructose in the mainstream glycolytic pathway in liver. Remember, this enzyme is very important. That is this fructose 1-phosphate aldolase enzyme. If this enzyme is deficient, we represent by using a minus sign. If this enzyme is deficient, you know that this product will get accumulated and this will not be utilized at all. So therefore, accumulation of these products can cause damage to a body, a system. So therefore, this is a genetic defect. Okay, and what will happen if this enzyme is deficient, or this enzyme can also be deficient, fructokinase? What will happen is lot of fructose 1-phosphate gets trapped. In other words, phosphorus gets trapped. Okay, so that can lead to acidosis, activating glycolytic pathway in a faster manner, and it can lead to acidosis in the body. So this situation, due to deficiency of fructokinase and fructose 1-phosphate aldolase, leads to fructose intolerance, and it is a genetic defect in certain individuals. Another monosaccharide which enters into the mainstream glycolytic pathway is mannose. Remember, mannose is a C2 epimer. Let us write the structure of mannose here. So at the second position, this is position number 1. This is the structure of mannose. So mannose can enter into glycolytic pathway very easily. Hexokinase can act on it. So therefore, hexokinase ADP. So you will get mannose 6-phosphate. Okay, once mannose 6-phosphate is produced, now this is an epimer of glucose. Remember this. Now this mannose 6-phosphate can be converted by using phospho-mannose isomerase enzyme. Okay, phospho-mannose isomerase enzyme will convert mannose 6-phosphate into fructose 6-phosphate. Now remember, fructose 6-phosphate is an intermediate in the glycolytic pathway. So this way, mannose can very easily enter into glycolytic pathway. Pentose is the next carbohydrate that will enter into glycolytic pathway. Now pentoses will be converted to either hexoses or trioses. So we will be looking at how pentoses can be converted to either hexoses or triose phosphates, hexose phosphates or triose phosphates, when we deal with the pentose phosphate pathway. The last molecule which is derived from fat that can enter into glycolytic pathway is glycerol. So we have seen a little while ago that glycerol will be converted to glycerol 3-phosphate by glycerol kinase enzyme. Okay, so once ATP, once glycerol 3-phosphate is formed, this can very easily be converted to dihydroxyacetone phosphate. And this is by glycerol 3-phosphate dehydrogenase enzyme. Okay, so therefore this is NADH plus H plus. Glycerol 3-phosphate dehydrogenase can convert glycerol 3-phosphate to DHAP. Now once DHAP is formed, we know that this can be converted into glyceraldehyde 3-phosphate using triose isomerase enzyme. That is, glyceraldehyde 3-phosphate is a component in the center pathway of glycolysis. So this is how all the monosaccharides enters into the mainstream glycolytic pathway. So we have looked at fructose, we have looked at galactose, mannose, pentoses and glycerol. Let us look at how polysaccharides enters into the mainstream glycolytic pathway. So the two polysaccharides are, one is glycogen, another one is starch. So you know that structurally they are very similar except in the branching. So now they will be acted upon by amylase. So there are two kinds of amylases, alpha amylase and beta amylase. Amylase can act on them and can result into maltose, maltotriose, okay, and glucose units. So this is how they are broken down into smaller units. Now once you have now these disaccharides like maltose, lactose and sucrose. So these are the three disaccharides which are commonly found in our diet. So maltose will be acted upon by maltase and you will get 2 units of glucose. Glucose, there is no problem, it can enter into regular glycolytic pathway. Lactose will be acted upon by lactase enzyme and you will get 1 glucose and 1 galactose. Glucose, there is no problem, galactose pathway, we have seen it. Sucrose will be converted to 1 fructose unit and 1 glucose unit. Glucose, there is no issue. Fructose, we have seen, is the 2 different pathways, one that is taking place in liver, another one which is taking place in adipose tissues and in muscle. So let us write, this is maltase, this is lactase enzyme and this is sucrase enzyme. So this is how polysaccharides, disaccharides, all of them enter into the mainstream glycolytic pathway. So all this combined thing is known as feeder pathways to carbohydrate metabolism.